Cool. So today I will be talking to you about optimizing machine learning prediction queries, and not only prediction queries on modern data engines. First, a couple of words about the group I am in. So it's called Gray Systems Lab. It's an applied research group embedded in the product. So it's part of Azure Data. We have a broad focus on systems, databases, machine learning research, and our goal is to deliver to our products to have open source impact and as well as academic impact through publications. We are about 25 scientists, research engineers, and data scientists in the group right now. This photo is quite a lie because it was pre-pandemic, so it misses a lot of people, and also a lot has been reshuffled during the pandemic, so people are all over the place. Still, some faces are there. So let's see a bit. At GSL, we have, as I said, a broad range of areas. On the ML-related side, we have what we call enterprise-grade machine learning. So this is more the systems for ML. We also have a lot on the ML for systems like learned cardinalities, optimizers, in general systems, configuration, and so on. Today we'll be talking about the enterprise-grade machine learning part. And with that, let's see a bit what is the dream of a data scientist. So every data scientist wants to feel that they're doing everything on their laptop, while automatically, magically, everything happens, in the clusters and so on in the background. So to make that a bit more concrete, we have two personas. We have a data scientist and we have an analyst developer. So what the data scientist wants to do is to train model on their laptop and share them with the rest of the world to use them. Now, on the other end, we have the analyst, the data engineer, and so on, the developer that wants to use the various existing models to make predictions on new data. And but sadly, this is a very small part of the story. Anecdotally, they say that only 20% of the data scientist time goes to training your data. So we have a lot more going on there. So first, we have the data exploration phase, which is an iterative process to find the right data, clean them, prepare them, and so on. Once you have that, you do your model training, which is, again, as we know, an iterative process. You come up with your best model, and then you deploy it somewhere in Azure ML, locally, doesn't matter. And then on the other side, we have, again, all the data selection and various transformations that have to be done specific to the inference. By the way, I will be using scoring, predictions, inference interchangeably here. And so you do your data selection and transformation. You get your model from a repository, and then you do the scoring based on the new data. We have identified in our GSL various areas that we are currently working on. One is on the data preparation, data integration side, so data cleaning, how do you combine data sets, how do you do featurization? Another area is SQL, is on the, essentially, how do we do the computation? The two main contenders here is SQL and Python. We want to scale the computation, we want to support different engines, be it your analytics database or Spark and so on. Another big area is how do we do better model scoring? So how do we support various model types? How do we do end-to-end pipeline optimization? And how do we do hardware acceleration? And the fourth area is provenance. Governance, you have all the different models. So now not only you need to have data governance, but also model governance, right? And impose policies and so on. Today, I will be focusing more on the model scoring side of things. And with that, let's see a motivating example. So you have this query that says, of course, it's about COVID. It says, find all the patients that have asthma that are expected to, that it is highly likely that they're going to develop a severe COVID-19 case, right? How would you do that? Let's say you have a lot of data in your database and you have three main tables. So you have the patient information, you have the pulmonary tests of the patient, and you have various blood tests as well. So what you're going to do here, you see, this is a SQL statement, the first part that is essentially selecting this data, right? So imagine you're a hospital, you have all this information, you're going to join them and use them for inference. You have various patients, and let's say every morning you want to see who is expected to be a severe case, right? You have your data, and then part of the pipeline now is you have a trained pipeline that you have trained based on all the hospitals in the country or across countries and so on. So it's a tree classifier. It gets various features. It can get your BMI, whether you have asthma, hypertension, and so on. It does some featurization, scaling, one-hot encoding, etc., concatenates, and then it's a tree classifier. So we use that. This is the syntax we use in SQL Server. So essentially, you see this predict statement here. We're saying I'm going to be using this model, this Onyx model, which is called COVID risk, with this data that you see above from the joining of the data. And on top of that, I'm going to be having two predicates. The one is that the asthma has to be true, and then that the COVID risk has to be high. And then I will be returning these patients, right? So this is a prediction. This is a batch prediction query, essentially. Why do we care about batch prediction queries? So here's the motivation. So first of all, what we have seen is that scoring drives big part of the cost of ML in the enterprise. The reason is that, yes, as we all know, training takes much longer, needs more resources, but then you train your model once and you're going to be using it millions of times for predictions. A second point is that we have a lot of pre-trained models nowadays. We saw in the previous presentation, YOLO, or the GPT-3, and so on. So again, we don't need to spend resources on training because we have all these pre-trained models. And anecdotally, it has been shown per estimates, like this is not something I can confirm from Microsoft. For example, there is an Amazon report that says up to 90% of the ML cost in the enterprise is due to model scoring. What we have shown is that batch scoring is very important, and very often for enterprise customers, it's the preferable way, or at least it's efficient. So we saw that in 130 customer engagements, 91% of them were covered by batch processing. So this means that you don't need real-time millisecond latency. You can just every so often. And by batch, I don't mean once per day necessarily. It can be every few seconds or every few minutes, right? And an additional 6% was okay with batch at short intervals, right? So a big part, batch scoring is really important. And the third point that is important for motivating this work is that traditional machine learning is the most widely used when it comes to structured data. So by traditional machine learning, I mean all your non-DNN, essentially, models. This can be linear or logistic regressions, all the tree-based models, random forests, gradient boosting, light GBM, and so on, and various featurization operators. So based on a Kaggle survey last year, 80% of the responders said that they're using traditional machine learning, and this can be opposed to 43% of them using deep learning frameworks. And we also did an analysis of 10 million GitHub publicly available notebooks. You can see a version of this on archive. We're having the latest GitHub data, and we will be published that soon. And you will see there that less than 20% of the users are using deep learning frameworks. So that is to say that we will be focusing on batch inference queries, batch prediction queries that are using mostly traditional machine learning models for our optimizations. Now, let's focus first. By the way, how much time do I have? Until when are we?
We have a hard deadline at 5:30, okay, which we would like to use questions in that interval. Perfect. So yes, let's say you have half an hour nicely.
Perfect. Okay.
But you can use as much as you want, sorry.
Thank you. So first part, let's see, how do we execute this query, right? And the main takeaway here is to bring models closer to where the data is. So we have this baseline approach of prediction queries. So this is a typical scenario that you usually have. You have a user, you have a web server, you have a database where all your data are that you're going to be using for inference. And then you have somewhere containerized a model with probably some featurization exposed as a REST API. So the user is contacting the web server, is getting the data for inference. So here, this could be your patient data. gets back the data, and then also sends the data to the container in order to do the predictions, right? Gets back the results, probably updates the database, caches some of the results, and then returns the results to the user. Now, we see a few problems with this approach. And then also, if you have multiple models, you're going to be having multiple containers and so on. So we're lacking a lot of enterprise features which are really important. So first of all, it's security. So the data and the models are sitting outside of the database, which means, first of all, the data movement can be a no-go for many applications, be it healthcare or banks or anything you have. So you might not even be allowed to move data outside of the database. In addition to that, we have extra infrastructure because, as you can see, we have the database, we have the containers, and so on. And we have lack of tooling and best practices that come with all these decades of using databases. And on the other front, we also have a hit on the performance side, of course, because we have to move probably terabytes of data or more, which increases latency and decreases throughput when it comes to batch inference. Now, instead of that, what we are suggesting, what we have done actually, is to integrate essentially the runtime, the machine learning runtime with a data engine, right? So what this gives us is that now the web server can go directly to the data engine, both your model and your data residing there, so you don't need to move any data outside of the boundaries of the database. Of course, this comes with all the security guarantees, which is super important. It reduces existing infrastructure, all the best practices and tooling that come with it. What about performance, though? As I will show you throughout the talk, what we managed to do is, if you do that on top of Spark, we can get up to 13x better performance if we enable also a lot of optimizations. And on SQL Server, it's up to 330 times faster. If you're wondering why faster on SQL Server, the reason is that if you unlock some optimization, SQL Server's optimizer is smarter to do even more. So that is the main reason. So let's see about the execution still. What we have done this last couple of years to execute prediction queries inside our Azure Data engines. I saw you still hear this prediction query that we had before. So on SQL Server, we have this predict statement. This has been there since 2017, but it was focusing on very, very few models. So what we did now is we embedded Onyx runtime within SQL Server. So this means that you can you can store your models, your Onyx models inside the database, and then you can use Onyx runtime to score them where they are without moving any data. This is available in SQL Server in Azure SQL Edge, as well as the SQL DW. So the SQL DW is the data warehouse. So think of it as the similar with Snowflake, Redshift, and so on. So that's the part of Azure Synapse Analytics. Second, recently we have introduced this predict operator to do scoring in SQL in Spark as well. So this follows a similar syntax with SQL Server. And the interesting thing is that we can now support many different types of models. And our North Star goal, why focus on SQL Server and Spark? Actually, part of the Azure Synapse Analytics is that we have these two main engines that we're focusing on. So it's SQL DW for analytics and Spark for all the rest. And North Star goal is essentially to support any model on any engine. We have a lot of work going on there. I will focus on some challenges rather than the solutions here. So on the any model type, essentially what is important is to have a common representation. So can you have a common API to do all the predictions? And for that, we are betting on MLflow. This is coming from Databricks. Essentially, you can see it as a wrapper out, wrapping models that can, it supports scikit-learn and PyTorch and TensorFlow and many others. When I talk about APIs, it's important, do you do it through Python or do you do it through a REST API? And with that, a second challenge is data movement. So between the data and the machine learning engines, how do you do that? Do you do a text-based? Is it binary? Do you use arrow? Also, I lied to you a little bit before by saying that we can bring everything inside the database. There are still cases that we cannot for a few reasons. First of all, you cannot embed any runtime inside the database. That would be a nightmare in scaling and being able to support many different engines. So still, our idea is that you will have one or more engines embedded in the database, and then to support more models, you will have also remote models. The other reasons for having remote models is that models are getting bigger and bigger. So as long as you have DNNs, this can be too expensive to download in the database and so on. So still there need to be remote execution. So the local is the fast path, but then you can also have remote execution. Third part is model lifecycle management. So how do we integrate with a model registry such as Azure Machine Learning? Like we saw in the previous talk, you can have multiple different models and so on. How do you publish them? How do you integrate with all this ecosystem, essentially? And the fourth part that is we find it being super important is how can we enable containerized execution of models? So this is related also to library dependencies. You can have a scikit-learn model. Let's say you integrate scikit-learn with your data engine, right? You have one version of scikit-learn, but your model is trained in another version. How do you support that? Or let's say you are in a cloud environment, they give you one version of Spark and a version of TensorFlow, but you want to use another one. Your model is not compatible with that one. How do you do this? It sounds very engineering, but it's very important to get that right. And also, how do you do all that in the most efficient manner, right, when it comes to containerized execution? So essentially, with containerized execution, we can do any model with any language bindings across any engines. So we are looking into that a lot. And with that, let's turn to Raven, which is essentially our optimizer for doing all this. So optimizing prediction queries. This is the bigger picture here. So like we said before, we have data plus models coming in for doing the predictions. What we are doing is we are having a common intermediate representation where you can have both data and machine learning operators in the same structure. Then we have the Raven optimizer. So the Raven optimizer gets this intermediate representation and does various optimizations that I will talk about next, returns an optimized version of this IR, which we then translate to a SQL statement or an optimized plan, essentially, that can run on Spark or on SQL Server, which have been integrated with machine learning runtimes, and it can run on various hardware. So for now, we have looked into CPUs and GPUs. So the very initial vision of this was presented in Cider in Amsterdam close to 2 years ago. We have come a long way since then about like making these things real. So everything you see here is fully implemented, and we have added new things and so on. So there are two main types of optimizations that I will be talking about. So it's logical optimizations. I'm saying it in a database, fashion. So it's logical optimizations and then logical to physical optimizations. Let's take a look. I will present two logical optimizations. The first one is the predicate-based model pruning. So essentially here, what we want to do is to get information from the data part, for example, predicates in this specific case, to optimize the machine learning part. So essentially, we're going to be opening up the machine learning part, looking at the predicates from the data part, and try to push them inside the model to optimize it. So in this case, you see three phases of the optimization. You can see the tree classifier on top, and then below that you have the 4 features. We're oversimplifying here, but essentially it's a projection that tells you get the age, the ppm, asthma, and hypertension. Then you also have an asthma be true, right? So, and you see that asthma is one of the inputs to the model, to the pipeline, and then to the tree, right? So in step 2, what we're doing is we're completely dropping asthma. So you don't even need to read it from the database. And we are substituting that with a constant. You can you see my mouse pointer? Or you do? Okay, perfect. So you can see here that we have substituted asthma here with a constant that this is always going to be true. And then what we are going to do is we will try with various rules to propagate that all the way to the tree. So essentially, you have your one-hot encoding here. You will accordingly say, try to push that information higher up, and then through the concatenation, and then coming here, what we can see is that this feature, this root feature, was actually about asthma, right? So we know that this is going to be true. So only the left side of the tree is going to be needed. and we can prune completely the right-hand side of the tree. So we simplify. So we achieve two things here. The first one is we simplified the tree a lot. And the second one is that we avoid reading from the database this feature. So this is one optimization, which is the data to model optimization. We have a few more. So this one is interesting. It's called data. We call it data-induced optimizations. So essentially, we can look at the data, look at the statistics, and even if you don't have that, let's say, age is more than 30, then maybe you can look at your data and then see that indeed all the patients have are above 30. So in this case, you can do more optimizations for predicates that were not there explicitly, right? And what is even more interesting is, for example, if you do that in Spark, if you have a partitioning scheme, then you can get even fancier and you can be like, okay, I will compile a different model, a different plan for every part of the pipeline, for every partition, right? So because I will have different statistics, you can look at your Parquet files, for example, and then have a different way of optimizing each partition. A second logical optimization is what we call predicate-based model. Sorry, that's a typo. So the second one is the projection pushdown. So this one is about passing information from the machine learning part to the data part. So what we're doing here is we're looking at following the example before. Now we have removed a lot of features from our tree, which means that a lot of them coming to the feature extractor are no longer needed. So if you see, we also removed, apart from the asthma that was there, we also removed BPM. So the idea here is to go the other way. So we try to push that projection all the way down. So we have this tree classifier that no longer needs all the features it's getting. So how can we then push it all the way down to the relational boundary, essentially, so that then we can add this, we can remove this BPM from the projection. This in practice has been very applicable because, for example, we opened up, we analyzed more than 500 models from OpenML, and we saw, interestingly, that 46% of the features used in the models remain unused, actually, which was to our surprise. So this means that you have a lot of features. You're training a tree, for example, but then you not really the way the tree was. Let's say you have a depth of 5, and the way the tree was trained, you don't really need many of the features that you trained with. So on the logical to physical side, we have two main optimizations. So the first one is ML to SQL. So essentially, we have some rules that can turn a model to an equivalent SQL statement. And why is this logical to physical? It is logical to physical because essentially you no longer need the ML runtime. If you can manage to turn the whole model to a SQL statement, you can completely drop the model and simply have a pure SQL statement. Another one is the MLODNN. So this is through a project called Hummingbird. I will be talking about this very briefly in a moment. So essentially, the idea here is that we have these traditional machine learning models, think of it like a tree, and we can turn them to an equivalent neural network. And we do that so that then we can execute that initial tree to a modern DNN engine, which can take advantage of GPUs, for example, out of the box. While in traditional machine learning, it's very hard to get hardware acceleration like GPUs. So having these two strategies, these logical to physical optimizations, now we have a few questions to answer for each prediction query. So the first one is which runtime to use. So do we use the data engine, so we turn everything to SQL, or do we use the machine learning engine? And if so, do we continue using the traditional machine learning model, or do we turn it to a DNN? And on top of that, we need to choose what type of backend we're using. Are we going to use the CPU, or if it's available, we're going to use a GPU? And for that, we have many different strategies. So we have played with 3 different strategies. In order to avoid hard-coded rules, we have a few data-driven strategies. So this very briefly, this shows that, again, we're looking at these 500 models from OpenML. They vary greatly. So here you can see the percentile, the different percentiles, 5th, 95th, 25th, 75th of number of operators, inputs, features, the 3 nodes. So you can see it varies greatly. So this is to say that we cannot simply hard code some rules and be done with it, or we cannot just heuristically push some rules. So instead, we have trained some models. I'm not going to get into details for the interest of time, but essentially, you can see here so on the right hand side, you can see the optimality compared to if we try to do all possible ways and pick the best one manually, as opposed to what our model would give us. So you can see, for example, the classification based is very close to the optimal one in most cases. Okay, very briefly, the idea behind Hummingbird and how we can turn trees to neural networks. This was an OSDI paper in 2020. So you see this simple tree here, we're going to turn it to a neural network. How do we do that? So we put labels to the trees, to the internal nodes of the tree and to the leaves. We create this simple neural network with one hidden layer. So we have all the features on the left as the first layer, all the features that participate in the tree. In the middle, in the hidden layer, you have all the internal nodes that make the various decisions for the branching. And on the right, you have all the leaves, the 5 leaves. You are connecting them the way the tree is connected, and you have also this bias for the thresholds. And then you are connecting all the internal nodes to the leaves, right, based on the branches. So the idea here now is that this will give you the same result, but it does a lot more work. So it's kind of counterintuitive. And the reason it does a lot more work is because in the neural network, we're going to be evaluating all conditions at the same time, and we're going to be evaluating also all paths at the same time. However, it turns out that if you do that in a GPU, you can get, because of all the parallelism and all the efficiency and all the compiler techniques that can be applied, you can get very big performance speedups by turning that to a neural network, doing that extra work, but enjoying the parallelism that the GPU can give. This is our implementation on Spark. The main takeaway here is that we have developed it as a Spark extension, and the reason is that we can this way plug it in any existing Spark installation, so you don't need to change your bits in the Spark cluster. Any existing Spark cluster can use that as a, you just have a zip that has your additional files, and that's about it. And we have extended the session so that we have this predict operator. The other key design point here is that because we want to do our optimization in Python, or our optimizer in Python, because all the tools and manipulation of the trees and the models is in Python, we have a single Scala rule, which we call this Raven rule in the Catalyst optimizer, and this one in turn calls all our rules internally in Python. So some evaluation results. So this is Spark, this is Raven on Spark against Spark ML. So this is Spark with a default way of doing the predictions, and Spark with doing the predictions in scikit-learn. This is a 5-node cluster for worker nodes. So you can see 4 different data sets. The first 2 are a simple scan, and then you do the model. So we have 3 models: linear regression, decision tree, and gradient boosting tree. And the second 2, the expedient flights, also include joins. So this is a 3-way join and the 4-way join. So as you can see here, Raven compared to Raven without optimizations, we get a speed up of 1.4 to 13x. Compared to Spark ML, we can be fast up to 48x faster. And compared to Spark with scikit-learn, we can be up to 25 times faster. Now, the other thing we have done is, although the implementation is in Spark, we have taken these Raven plans and turned them to SQL statements to see what we can do on SQL Server. So you have Raven, you have the vanilla SQL Server, which is without optimizations. The DOP 1 and 16 is the degree of parallelism. So whether you use 1 or parallelism of 16, this is a 32 core machine. And also we compare with Madlib, which is on Postgres, which is one of the most common ways today of doing this type of prediction queries in a database. So compared to SQL Server, we can be up to 330 times faster. The reason is this is especially for simpler models where you can turn everything in SQL. And then especially when you have, for example, joins, you can even push down various parts of the model, even below joins, right? But then you also have big speed ups also for the rest of the models, especially with the projection push down that we mentioned before. And compared to Madlib, we can be up to, first of all, it could not run for the second, like for expedient flights. This is because it was generating too many features. It has to materialize them, so it couldn't finish. For the other two that it finished, we are more than 100x faster. And one of the reasons that Madlib is getting this toll is because it needs to materialize also a lot of intermediate results, plus it does no optimizations. And briefly about the GPU support, GPU acceleration. So here, one important point here is that when it's simple models, GPU is not worth it. When it's more complex models, so these are gradient boosting models with up to 500 estimators and a depth of 8. So here we can get another 8x speed up by using a GPU, as you can see. And the more the higher the complexity, the better the speed up. And with that, so we're done with Raven. Let's look at a newer project. We call it Surakav. So the idea here is, can we use, like now that we have brought these Tensor runtimes inside our engines, can we use them for accelerating things beyond ML, right? So we have a vision paper in VLDB this year, but we have done a lot of work since then. So what you see here is actually the first time we talk about it publicly. This is the picture you have today with what we have done with adding, for example, Onyx runtime inside our engine. So you have SQL, this is in Spark, you have your Spark SQL, you have your Spark Catalyst Optimizer, then you have a Tensor runtime, which can run again on CPU, GPU, you can have FPGAs, custom ASICs, and so on. So what we're doing here is we're adding an extra layer, which is Surakav. Essentially, here are the key ideas. So columnar data can be mapped to two-dimensional tensors. And then what we're doing is we're turning relational operators to tensor operators. So we're re-implementing these relational operators to tensor operations. And with that, we can take advantage of any hardware consciousness that is provided by the Tensor runtime. So to make this a bit more clear, what are the benefits here? So why are we doing that? So Tensor runtimes have been, used throughout the years to super optimize them for different types of hardware. So they contain all the operators needed for, you have your NVIDIA GPU, you can have any other GPU, you can have different FPGAs. So by us doing this translation from relational operators to tensor operators, we no longer need to implement all the custom kernels for every different hardware you have, right? So we're avoiding all this explosion in implementation. And at the same time, Tensor runtimes have been super optimized with various compilers and code generation and so on to make them as fast as possible. So the idea would be not to be faster than, manually implementing everything for this custom hardware, but using Tensor runtimes as an abstraction to do that equally fast or comparably, let's say. That would be the gain here by avoiding all this implementation effort. So two main challenges. The one is expressivity. So can we cover with the existing operators of PyTorch, for example? Can we cover all relational operators? What we have done during the summer is we have support for many different operators. So we have selections, filters, joins, group bys, aggregates, sort, case statements, in statements, subqueries, some string, also manipulation. We can currently support 19 out of the 22 TPCH queries. And in terms of performance, what is interesting in doing this translation is that we have to change the way we're thinking. So instead of, what is very important is to keep this tensorized implementation of the operators, because essentially whenever you start doing loops, that's when you lose the parallelism of the GPU. So you need to do that as much as possible in a vectorized fashion, right? So that is what is interesting and intriguing here. So I'm not going to get into more details of how we do these translations, but I will give you some very preliminary results of the current version of Surakav. These are 19 queries. You will see some are missing. 3 are missing. So you can see already that why are we comparing? We cannot spill to disk yet. So this is TPCA scale factor 1. It's a single core, right? So this is our current version, our current proof of concept. So you can see already that we are comparing against Spark because we are using Spark's optimizer. So we use Spark plans that we turn to a PyTorch model. Almost always we are as fast as Spark, and very often we're much faster than Spark. So that's the first takeaway, which is very interesting, very promising at least. And then let's see a bit. This is all on CPU. Now this is a bit more interesting and apples to apples comparison. So here we have TPCA scale factor 10. This is 3 queries that we have taken and tried to optimize them to see how much we can get, right? So we are comparing Surakav with DuckDB as one of the best in-memory databases for CPUs out there right now, and Blazing SQL, which is by NVIDIA, which is on GPUs. So they have SQL and with Rapids and so on, they can turn that to, but it's only for NVIDIA GPUs, of course. So we have CPU 1 and CPU 6 means we're using either 1 thread or 6 threads. So first you can see that we are comparable to a high performance CPU implementation. So DuckDB is faster, is comparable for 1 thread on Q1, is faster for 6 threads, but then we are faster for Q6 and Q14. Q1 and Q6 have no joins, Q14 has a join. And then when it comes to GPU, we can be much faster. Which is very promising. Again, these are 3 queries, but like we can be fast. We can be, let's say, comparable to state-of-the-art in-memory CPU engines. We can be faster on GPU, and then compared to Blazing SQL that only works for NVIDIA, we're actually faster right now. So these are the current results. They're not complete, but they're promising, and we keep on working on it. And to wrap up, 3 main areas that I touched upon today. So the first one is execution of prediction queries. So main ideas are to bring models closer to where the data is and embed machine learning runtimes inside the data engines whenever that is beneficial and so on. The second one is with Raven, the optimization of prediction queries. So I talked about logical and logical to physical optimizations. We have an end-to-end implementation in Spark, and we have different strategies to pick up the right optimizations. And I showed you performance improvements up to 13x over Spark, the same plans up to 330x over SQL Server. And then last I touched upon how can we use Tensor runtimes beyond ML. So we discussed how we can offload relational operators to machine learning accelerators now that we have them next to the engines. This way we can leverage compiler advancements and modern hardware to speed up relational operations. And we have promising initial results against Spark, DuckDB, and Blazing SQL. And thank you.